and gentlemen, thank you very much for giving me voice. Today, I will be talking about work published in 4 years ago, but very important due to high citation level. Almost recited his work 77 times, so it's very important. The work is cooperation of Korea University, Hanyang University, of Professor Ki Hyun Kim, and with cooperation with Professor Pravan Kumar from Kolkata University. The work is entitled Current, Progress and Challenges in Photoelectrode Materials for the Production of Hydrogen. The question of this article is to show the recent advances achieved in photoanides cathodes for PCC water, splitting our viewed. Key challenges in the fabrication of highly efficient and stable photoelectrodes are explicated. Deliberations are also given on emerging photoelectrode materials for photoelectrode water splitting, strategies and outlook for driven devices are highly delighted. The development of alternative clean and renewable fuels has become the need of the hour due to the decreasing supply of fossil fuels. Solar hydrogen produced from water is sustainable green substitute for fossil fuels for a variety of applications: transport, power generation, industrial energy. However, cost-effective, efficient, and stable production of hydrogen fuel from water is challenge for real-world applications. In pursuit of cost-effective, large-scale commercialization of, for example, photo production of hydrogen from water, attempts were made to describe and data up-to-date knowledge on photoelectrochemical water splitting processes. This is effective options with space of semiconductor photoelectrons of the base splitting processes. Energy is key to affordable, clean, safe, and habitable conditions required for better standards of living. The total energy resources available worldwide are generally declassified into nuclear, fossil, and renewable ones. In case here is not yet described as to the core, because core were in 2 years. Therefore, to meet today the amount of energy and to have associated environmental issues, they keep to a cost effective. The forecast is that depletion of coal, the oil will soon, mostly by 2060, 190, depleted. So gas would be 200 years later. So the trouble is we have to use new fuel sources and electrolysis due to potential of using renewable sources like solar energy, which are also influence wind, geothermal, and hydro. This can be efficient of hydrogen fuel. Also biomass, which is mostly plants, is also so biochemical is also so. Photovoltaic approach has emerged as well. Numerous processes, including thermolysis, electrolysis, biomass conversion, and photolysis, have been reported for hydrogen fuel generation from water. All these processes have several advantages and disadvantages compared to others. A detailed assessment of these processes is beyond the scope of further this review. Further, the United States Department of Energy has priority pathways for the various processes for hydrogen generation. This figure summarizes for future prospects for development of the sustainable large-scale generation system for hydrogen. It generalizes the possible process for hydrogen generation into three, namely near-term, mid-term, and long-term. Currently, 96% of hydrogen generation is associated with fossil fuels, methane and coal, a feedstock where 4% of hydrogen is produced through direct water electrolysis. Therefore, the current efforts related to increasing hydrogen production from water to reduce their dependency on fossil fuels. Furthermore, hydrogen generation from photoelectrode water splitting is considered to be one of the most effective options based on long-term strategies by the US Department of Energy. Although a number of reviews have been published to describe the progress of solar-driven water splitting, they have largely been confined to limited subjects such as the material aspects of the photoelectrode. This is the most important issue in determining the future pathways for developing efficient and stable hydrogen fuel cells for large-scale hydrogen generation. We focus on the evaluation of the performance of different or to help maximize the efficiency to promote the commercialization of such techniques. We classified positive photoelectrodes as in poor photoelectrodes with hydrogen splitting efficiency lower than 1%, marginal, higher than well acceptable from 4 and 10, and highly efficient above 10%. We've further discussed the future of prospect of scaling these developed photoelectrodes for large-scale hydrogen production from water. The splitting of an hydrogen molecules requires Gibbs-free energy of 237 moles kilojoule per mole. Therefore, the response to free energy, temperature, and heat respectively, the required energy can be supplied by heat demand respectively. The required energy can be supplied by various types, depending on the power types employed, the methods of water splitting can be classified. Photocatalytic water splitting is also known as artificial photosynthesis, as it mimics the natural photosynthesis processes. The radiation photocomposes the water into hydrogen and oxygen. However, the selection of semiconducting materials is crucial to obtaining the overall photocatalyst water splitting. The semiconducting material absorbs the solar energy and transfers it to the water molecules for decomposition into hydrogen and oxygen. Must have the following three properties. The semiconducting materials should be stable in aqueous solution. The band edge, example conduction band minima and valence band maximum, must align with the quarter readers. The mass must be higher than 123. The efficiency of 2 volts, electrovolts. In photoelectrocatalytic water splitting, the photoelectrodes can be produced as in contrast, which produce a negative current density when negative potential is applied, are known as photoelectric catalysts. Further, the conduction band minima should be more negative than the reduction potential, whereas the valence band maxima should be more positive than the oxidation of reduction potential. Due to the band edge absorption of higher photonic energies, the photocatalysts with a band gap in the ultraviolet range better than in visible region. As the ultraviolet region will consist of only 4% of the solar spectrum, it is a big challenge to require high efficiency photocatalytic water splitting. In contrast, the visible 800 and infrared portion of the solar spectrum accounts for 96% of the total solar energy. Therefore, harvesting hydrogen from visible light can be an efficient solution as far as water splitting driven. The splitting can be performed in 2 or 3 electrode setups immersed in an aqueous electrolyte, among which one of electrodes must be photoactive under solar radiation. The 3-electrode setup consists of 2 active electrodes, photoanodes and photocathodes, and third reference electrode, for example, silver chloride. Under solar radiation, the active photoelectrode generates electron hole pairs, which involves for electrochemical splitting, where electrons go to the cathode for reduction, hydrogen generation, and photogenerating holes remain on the anode oxidation. Consider the photoanode as an active electron that is exposed to the solar spectrum. The half reactions of electrochemical water splitting can be described as follows. 123 electrons are required, and here in case of is up to Gibbs energy 237 kJ per mole. So the excited electrons travels towards the photocathodes via external circuit of water destruction, whereas the holes of the photoanode drive the water oxidation. Lately, a number of semiconductor-based photoelectrodes have been reported to be proficient in generating hydrogen and oxygen from various splitting reactions under solar light irradiation. Note that various fault water splitting materials mainly belong to cell groups such as transition metal oxide group, valence band group, uh, gadolinium, germanium, synchronous 5, and metal halogens. Group 3 called perovskites. The standard splitting is uphill reaction at least 1.23 with a charged electrode toward the respective electrodes via external circuit and electrolyte. Charge transfer from electrode to electrolyte to facilitate the reaction. Furthermore, the felt stability in the aqueous solution along the band edge, straddling the water ripples in a key strait in the design of stable photoelectrons. Furthermore, bonds bending at the electrolyte interface is crucial to determining the type of electrodes as seen in Figure 2. Likewise, most of the n-type semiconductors have upward bending. At the semiconductor electrolyte interface, which actually creates the built-in potential for the conduction of band electrons. Due to these n-types as for photonals, Fourier electrodes water splitting. The host travel to the other electrodes of this p-type as photocathodes for photoelectric cathode water splitting reaction. The corresponding current is presented. Clearly charge transfer occurs in conduction band electrodes at the electrode's electrolyte interface, as Pi type are not responsive for oxidation. For the combination of different energy sources and types of semiconductors higher than the crucial design indicated a wide variety of like cyanides, sulfur acinides reported in what research. The efficiency standards are numerous efficiency reported for measuring performance of photoelectrode in photoelectrode catalytic water splitting. Generally, the solar to hydrogen conversion efficiency is one of the most crucial calibration efficiency for any developed photoelectrodes. The solar to hydrogen conversion is the largest impression on the hydrogen market price, defining the sustainable for the development of various devices. The Tornado's charts also emphasize the impact of solar to hydrogen conversion on hydrogen prices, such as 25 and 10% of solar to hydrogen. Efficiency is comparable from $2.7 to $5.6 per kilogram. This further certifies the importance of solar to hydrogen conversion of 10% has commonly been well thought out of as a tolerable efficiency. However, the techno-economic investigation indicates that solar to hydrogen conversion efficiency has been equated to 23%. In contrast, stable efficiency is 1 to 2%. The photoelectrocatalysts are responsible for the water splitting reaction 0 volts at 2 electrode setup. The diagnostic efficiencies, such as applied bias photon to current efficiencies, photon to current efficiency, and absorbed photon to current efficiency, are generally adopted to calibrate the performance of such photoelectrodes. After Solar to hydrogen energy as applied bias photon to current efficiency is the commonly established efficiency. This actually is the modified version of the solar to hydrogen conversion and the given applied voltage. For the cogent measurements, the measurement must be performed under the two electrode configuration. Follows. Here is the photocurrent intensity obtained under an applied bias. Is the Faraday efficiency is in the incident power on the active photoelectrodes. The standard solar to hydrogen efficiency represents response from the overall spectrum. The incidence of photon to current efficiency became a very important measurement to quantify the base of different wavelengths in the spectrum. This illumination power intensity gives, which is proportional to the photon to current efficiency, and reverse to illumination monogrammetric